Right, so example 2 now. We are going to use the same motor as in example 1, which is this here. I've just put back the information for you for your convenience. And we're going to reduce the field flux to 80% of its value by means of a field rheostat. That's just a variable resistor. So if you remember, this is a shunt configuration. So here we have VT, and this is the field current IF, and by controlling this resistor we control the field current. So that's all the field rheostat is. You simply have a variable resistor in the field path so you can control the current going through it. And we want to determine the new operating speed. So we know that the new phi is 0.8 times the old phi, which is 10.24 milliwebers. Now I'm going to put down some equations here for you. If eventually we want to find omega, which is a new speed, I know EA is equal to Ka phi by omega. So this is what I want to find. So in order to find that, I have to find the new EA and the new K phi omega. Now I can estimate what K phi, the old K phi omega was, because I have EA, omega, and omega m from the last problem. Or I could also use TE, IA, and K phi from the last problem. So I have TE, IA nu is equal to TE on K phi by omega nu. I substitute, here I'm going to substitute for K all of these values here, which come from my equation for EA, involving all the armature paths and the active conductors, the number of parallel paths and the active conductors and so on. And I have all of these values, so I'm just going to plug them in and I get what the new value is for IA. Of course, what I could also do is use the old values to find what Ka is. So for example, I know IA old was 73 amps, which was equal to TE, which remained the same, over K phi old. Now I know K phi new is 0.8 times K phi old. So I could say for the same TE, so I have TE is equal to K phi old by 73. TE remains the same. So if I change K phi new, TE is equal to K phi new, which is 0.8 K phi new. Then I have to multiply, 0.8 K phi old, which is K phi new. Then my current has to change to cancel that. So it'll be 73 on 0.8. And this 73 by divided by 0.8 will give me 91.2 amps as well. So that's an alternative way to do it. Once I have that, I could go ahead and find my new EA, because I have the same 230 volts, the same, I think it was 0.188 ohms, and I have now my I new. So I could calculate EA new, and that gives me 212.85 volts. And now I could calculate my new value of omega using EAIA is equal to TE omega, or I could use EA is equal to phi n ZP on 60A, where this is the same as 2 pi n on, sorry, it will be omega multiplied by 60 on 2 pi. So I could use either of these, or if I had found what K phi was from the previous example, using the information from the previous example, I could say EA is equal to K phi new multiplied by omega m, and I could simply solve because I would know these two parameters. So This is just going through the mathematics here, solving using this equation. I could also solve, well, I didn't put in the example for the solution using the other techniques, so maybe you could do those, and you'll see if you end up with the same result. So that would be an interesting thing to look at if you don't get the same result. So next example, we have a permanent magnet DC motor with the following parameters: KT, which is equal to KE, is 0.5. This is your K phi basically, and RA 0.35 ohms. Now how would we treat a permanent magnet DC motor? This would essentially be the same as a separately excited motor, because the field is not being excited by the power supply in any way. The field in this case comes from permanent magnets, which means they are not controllable in the way that an electromagnet would be. So we have no field current in this case, is just a permanent magnet. So the only resistance we have in the circuit is Ra. And now we have, for a torque of up to 8 Newton meters, you're required to plot the steady state torque speed characteristics for the following values of Va: 100, 75, and 50. So of course we have now our circuit diagram. And we have here 100, 75, and 50, and we have 0.35 ohms. So we want to find the torque versus speed characteristic for this. So we know at no load torque is 0 and Ia is 0. No torque, no current. And remember, we talked about this correspondence between torque and current. Omega m is Va minus RAIA on Ke. Remember, all of this is just EA, right? So EA over Ke, or in other words, EA is equal to Ke by omega m. So I simply now plug these into the equation. Ia is 0, so it gets rid of this. So I have Va on Ke, so I have 100 on 0.5, 75 on 0.5, and 50 on 0.5 for the various cases. Remember, Ke here is 0.5. And that gives me 200, 150, and 100 respectively. So my initial speed with no torque would be 200, 150, and 100. And then for a torque of 8 Newton meters, then I have I is equal to T on K. Remember, Te is equal to Ke I A. So now I could compute I by just simply using T on K, which is 16 amps. So I have a 16 amp for this load. I have a 16 amp current, and I have now to work out omega m. Again, I'm going to use V minus I R on K. So I have 100 minus 5.6. This is 0.35 by 16 over 0.5, 0.35 again by 16 in all these cases, 0.35 by 16, which is my voltage drop across the resistance, right? So I'm just finding EA here in all of these cases and then dividing by 0.5, so I get 188, 138, and 88. So if I want to draw the characteristics here, I could just go from 0 to 8, and then I have 200 to 188.5 at 8. I have 150 to 138.8, and I have 100 to 88. So I should end up with something looking like that.